Huh? Say it again. Yeah. So, yeah, sure. Yeah, sure. Yeah, go ahead. Someone, if you have any doubt, please ask me questions. Go ahead. I can listen. Vedant, they can speak also, right? Yeah, okay. Yeah, go ahead. Anyone having a question, please go ahead. It's a live session for clearing doubts regarding the course.
I have one query.
Yeah,
Hello.
please.
So,
Please.
the assignment 1 and assignment 2 both have the deadline 4th February, right?
Vedanta, do you know about this? Oh, yeah.
Okay, okay. I thought that 2 will have different deadlines. Okay.
Yeah. Anything else?
So, in probably you mentioned some reference book in the first lecture also, but I'm repeating. I mean, just wanted to know. Can you please give some reference books for this BCS things?
Yeah, yeah. Tinkham is the best one.
Okay.
Tinkham, Tinkham.
Okay.
That's the best one. And there is one more, which I don't remember much. But I have written a book, if you get somewhere in the library, on modern condensed matter physics. That also has a detailed description of BCS theory, including some experimental validation, etc.
Is it possible to get electronic copy of that book? I mean, it's a soft copy. I mean, the that book may not be available in our library. That's why I'm asking.
This thing. So Tinkham. Uh, Basically, it's a variational theory, and detailed in the class. So beyond that, it's all calculation. Some of the the sort of tricky things are the calculations of, say, the specific heat and so on, which are mostly shown in the class. Okay. Yes, all those who have joined, you can ask your doubts.
Yeah, actually, I guess the classes are very rigorous. So if we follow the reference books, then that will be okay. But I have
Ye-
some queries about the exam. So how, as it's an advanced course, how should we prepare for it? And can you give us any hint or suggestion about the exam?
yeah, I mean, the exams will be offline, okay, proctored offline exam by TCS, and these exams, the question papers will have a large overlap with the assignments. And there'll be also some scoring questions, which are numerical questions on superconductivity, such as calculation of, critical field beyond which superconductivity is destroyed. What is the, say, sketching of some phase diagram for type 2 superconductors, and so on and so forth. Okay, so everything you have to write on the paper is, and some of them could be, excuse me, some of them could be slightly longer in terms of, calculation of some quantities or getting some, some coherence length, etc., and so on. But if you follow this well, and these two books that I have written above, that should be fine.
Okay, okay, thank you.
Yeah. Anything else?
Another thing, the perturbative calculation for the electron-electron interaction while forming the Cooper pair via
Mhm,
phone,
mhm,
that
mhm, mhm,
part is not very clear to me.
mhm.
Can you give us some more, I mean, physical, or I'm not, I don't want the calculations, but
Mhm, mhm.
are not very clear to me actually. If you give us, if you enlighten us with some of your knowledge, so I think that would be better.
Yeah, yeah, yeah. So, first is that why do we first need electron-electron interaction? Because a non-interacting picture will not give you superconductivity. In fact, this is a very important difference between bosonic systems and fermionic systems. Bosonic systems will give superfluidity, even with I mean, without any interaction. Whereas fermionic systems, they do not condense into one, um, uh, like a giant quantum state, single quantum state. And that requires interaction because these are electrons, so they don't like each other. So because of Pauli exclusion principle, it will become very difficult for them to form a paired, structure. But for superconductivity, we need pairs. Now, where do we get the pairs from? The pairs will only come when you have these, like two electrons. If they directly interact with each other, you'll have a repulsive interaction, and that will never form a bound state or a paired state. So, to form a paired state, you need an attractive interaction. And apparently, who gives that? If and two electrons interact via an exchange of phonon, not directly, but by an exchange of phonon, then I'm saying phonon because phonon is the only uh, plausible option, because you're talking about a lattice, and the lattice excitation causes phonons, or phonons, I mean excitation of phonons and so on. So phonons are most natural for this in this particular case. So they
Purity,
need to interact. Tell me.
rather impurity, and there are various things that can also contribute, but the phonons are the most dominating part here.
Right, right, right. So I mean, when you have impurities and all that, it would be very difficult to get a paired state, because they would scatter off the electron, so giving rise to scattering states rather than bound states, like defects, homogeneities, etc. They would, create additional states in the superconducting gap, or in any, kind of vacant space where there's an energy gap, and will sort of scatter off that electron, giving rise to scattering states and not bound states. So phonons could be, as I said, phonons could be an option. That is what Cooper thought. And he wanted to show that this is indeed the case, that two electrons actually indirectly interact via exchange of phonons. And in that case, for a very short, sort of span of the interaction, or rather, sort of parameter range, narrow parameter range, the interaction could be attractive. And once you show that even there is a small phase space for them to have an attractive interaction, I think that then you're done. And this is exactly what he showed. And how would he show that? Because there is no other, energy scale in the problem so as to show. I mean, how do you get phonons? Phonons were very easily, thought from this isotope experiment. I think you have heard from the class what is isotope experiment. So if you take
Yes.
the two isotopes and calculate their transition temperatures, the transition temperatures depend on the masses of these isotopes via some relation. And these isotopes are actually indicative that the phonons are in the picture. I think I have told that in the class. See, there is this m to the power minus alpha, right? And alpha is equal to half. So it goes like 1 by root m. And if you look at the phonon dispersion in a lattice from the first course of solid state physics, that also one has the dispersion, phonon dispersion has a 1 by root m. So that is where, first time people thought that the phonon could be interesting. The next job is to show actually how this can happen. And because it's an indirect process, there has to, if there's a phonon involved, this has to be a second order process. So the electron does not directly interact with another electron, but it interacts with a phonon. And so if it's a second order process, can we do a second order perturbation theory in terms of the electronic interaction? Now, this not necessarily would work out, because if electronic interaction is so large that you cannot apply a perturbation theory, then of course, and this is what probably happens in this, high TC, that the electronic interactions could be large, and various other things. Your 2 delta by kT is not 3.5 as it comes out in or rather delta by kT is not 3.5 as it turns out for BCS, it's much larger than that. So, but here it works. And you do a second order theory, perturbation theory, and you sort of make the two electrons, so the electron interacts with a phonon, goes into a metastable state, and this metastable state relaxes into a fermionic state, by the same interaction. So it's that. So the initial state, and then your V in interaction, and then the metastable state, and then again the inner product, outer products. The outer product of the metastable states, and then again the electronic interaction, and then finally going into the final electronic states. It has an energy denominator. Now that's where the catch comes. An energy denominator has this ability to make something positive or negative. And that's what Cooper showed, that for a very small range of parameters, the energy denominator in a second order perturbation theory can become negative. And this is the crux of this attractive interaction. Okay. The calculations I have shown it in the class. So this was the idea.
Yes, and another thing, magnons can also be responsible for this.
Very, very good question. Very good question. Yes, magnons can be responsible, but in the sense that when you have a magnetic system and you have a stable, magnetic system, it usually, see, magnets and superconductors are like, the two sides of the same coin. It does not meet so easily, unless there are some iron-based superconductors which are only anomalies. So if you want to consider magnons, then you have a magnetic ground state. So then a superconductivity is not a stable ground state in that situation. So magnons are not excellent, possibilities for this. They could be. You could have very low energy magnons having where the ground state has some magnetic character, because you see the magnetism entirely originates from the electrons, and here the electrons are paired, forming a complete bound state, giving the net spin to be equal to 0. So if you think of the BCS ground state, it has no net angular momentum. So talking about a magnetic orientation is not a very good, justification here. So magnons are even being a possibility, but it is not a possibility here.
Okay.
Is that making sense?
Yeah. Thank you.
Yeah.
Hello.
Yes.
Actually, it may not be associated with the assignment, but from my curiosity, I'm curious to know one thing, that
Yeah.
is there any relationship between quantum confinement of electrons with the superconductivity?
No. In the sense that you can have superconductivity at macroscopic scales also. In fact, this is something that's interesting, that you have a flux quantization which carries h over e or h over 2e here. So this h is actually a prerogative of the microscopic state, whereas it happens at macroscopic scales. So why the quantum confinement is not a possibility, or it has no relation with superconductivity, is the following: that if you confine electrons more and more, the intervening energy level, I mean, the energy levels between, or energy spacing, energy gap, say, between two levels will keep increasing, because it's like 1 over L square. If you remember the first course on quantum mechanics, where one does particle in a box, you have pi square h cross square divided by 2m L square, where L is the length of the box. That's the ground. I mean, that's the energy between the two states, two successive states. As you make L to be smaller, this will become larger. So that is the thing that it says. So quantum confinement makes the quantum effects more pronounced. But these are still the scattering states, which means that they are of the form sine or cosine or exponential ikx, exponential minus ikx. You don't talk about a bound state there. But in superconductivity, you have to talk about a bound state. That's where the interest lies. So quantum confinement and superconductivity are two different things. In principle, they're two different things. It can happen that, in microscopic systems, you see superconductivity, or rather at very nanoscale, you see superconductivity. There is another thing that if you go to lower and lower dimensions, you may not have any order, superconducting order, because of some, theorem called as the Mermin-Wagner theorem. So you actually may need a three-dimension in order to have, superconductivity. Of course, I agree that these copper oxides are two-dimensional planes where mainly, the electrons form, they form pairs in the high TC superconductors. But that's again, that's not very well understood, that what was the role of dimensionality, where the phonons come from, whether there are at all phonons involved there. The ground state is not a metallic state, as we have discussed in your during the course, and so on. Is it clear?
Yes, clear. Thank you.
Yeah, thank you. Any other question? Anything else? I liked Sanhita's question about, uh, trying to physically understand why, or rather, what's the need for doing a second order perturbation theory. I think these are some of the questions that are never written in the books. And however, you try to make a book self-contained, it would not contain things uh, which can only be, taught in a class. Yeah.
Yes, sir.
Yeah.
Another thing, this is just a query. We have 2 more weeks, so
Mhm.
uh, so I just want to know how far we are going to uh, understand or discuss this superconductivity uh, in depth, actually. Uh, so, is there?
Yeah, I know. This is a rather short course. I mean, I have not really made it very long, and the main idea was to talk about BCS theory mainly. Okay, and that because I had a feeling. See, this is a very old course. This is recorded nearly more than 10 years back. Um, and I had a feeling, and the feeling is still there, that in many colleges, the BCS theory is not done. They simply say, superconductivity and Cooper pair and this and that, more like a story telling about superconductivity. So this I wanted to address. So in the remaining weeks, I really don't remember, but I did some, unconventional pairing, etc. That you could have more than S wave, you can have a D wave pairing, and you can, in that case, you can, decompose the order parameter to have different pairing correlations. And like, for example, the high TC is believed to be a D wave pairing. A D wave means L equal to 2, the angular momentum L equal to 2. L equal to 2 means, there are Cooper pairs with the up and the down non-zero distance. I mean, in BCS theory, they are actually at the same site. So there are D-wave pairing and so on. And then some, talking about some phase diagram, talking about some behavior of the physical quantities that comes out from BCS theory. Then one of the main, uh, feature of how do you understand that this is a superconducting transition. So the metallic specific heat according to this device theory, it sort of rises. Not device theory, sorry, it's electronic specific. It's according to that the linear in T kind of behavior. But then so you're coming from higher temperature. So it has a linear fall off. You remember that alpha T, right? T cube is due to phonons. That's called device theory. Then it falls, and then suddenly it jumps at the transition temperature and then falls some exponentially at very low temperature. So this jump at TC, that is the specific heat shows a jump. This is one of the distinguishing features of a superconductor. So this also comes out from BCS theory. So all these things are done and so on.
Okay.
It's a rather short course. I agree with that. It could have been made much longer, but uh, that was not the intent at that point of time.
Okay.
Anything else? Yes. Anything else?
Not from my side.
Say it again. Uh, I haven't opened YouTube. Can you paste the question here? And let me answer that question, and then I can. Oh, ceramic superconductors. Yeah, yeah. You can paste it back. Thank you. Yeah, exactly. Yeah. So since there are no questions, um, that at least we have gotten for the last 10, 15 minutes. So is it okay that we wrap up the session?
Yes, sir.
Yes, sir.
Okay.
No problem.
Okay. Okay. All right.
Thank you.
All right. All right. Okay.
Thank you.
Thank you. Thank you. Vedanta, thank you. Yep. And all everyone else. Thank you.